In this lesson, we will discuss sampling distributions and the central limit theorems. Let's take a moment to consider where we are in our journey into statistical reasoning. Generally, we know that we are trying to estimate parameters of a population. The most common parameters are population mean and population proportion. The big idea here is to draw a good, unbiased sample and use what we see there to make the estimate. To do this, however, we need to establish the relationships between sample statistics and populations. That's where sampling distributions come in. Let's suppose that we start with a population. For now, we'll assume that we know the population parameters. Later, we'll drop this assumption. When we take a sample from the population, the mean of the sample, x bar, is a random variable because its value depends on the sample that's taken. So, if we know that x bar is a random variable, what is its distribution? The distribution of x bar is called the sampling distribution of the mean. What we'll find is that the sampling distribution of the mean will, under appropriate circumstances, be normal, regardless of how the population itself is distributed. This is a pretty remarkable fact, and it is the basis of much of statistics. Okay, I'm going to jump into an example. Let me describe what I hope to show in this example. I'm going to start with a population and then draw several samples of different sizes from the population. What we'll be looking for are three things. How does the shape of the sampling distribution for the mean change with different sample sizes? What is the relationship between the mean of the population and the means of the samples we draw? And what is the relationship between the standard deviation of the population and the standard deviations of the samples that we draw? We're going to load the data from a population of the body mass in grams of male penguins during the guard stage. That's the stage when male and female penguins take turns overseeing chicks. We can start by taking a look at the shape of the population. Here we see that the male penguin body mass population is skewed to the left. Okay, now I've got a function that I'm creating. Don't worry too much about the code here. The function is called samp.means, and what it does is it draws m samples of size n. Then it returns a data array of the means of those samples. In other words, the function returns the sampling distribution. Suppose that we want to look at samples of size 5. I'll draw 100 samples of size 5. We'll save the means of those samples into a variable named sample5. So now we have a sampling distribution where the sample size is 5. Okay, we know that the population is skewed to the left. Will the sampling distribution also be skewed to the left? Let's take a look. It appears that with samples of size 5, we can still see some skewness. Maybe changing the size of the sample will have an effect. How about we look at samples of size 10? It seems like maybe there is still a little skewness here. Let's try samples of size 20. How about samples of size 30? Notice how the distribution is beginning to look a lot more normal. Since we're having so much fun, let's try samples of size 50. Here it looks like the sampling distribution is definitely normally distributed. So what's our takeaway? It appears that the larger the sample size, the more the distribution of x bar looks normal. Now take a look back at the histograms for the various sample sizes. Notice that they are all centered about around the same value. Looks like the center of the distribution is somewhere close to 4,140 or so. You know what number that is? Well, let's find the mean of the population. The population mean is 4,136.662 grams. So now we know two things. The distribution of x bar is approximately normal for large sample sizes, and those distributions appear to have the same mean as the population. A natural question is, does the same thing happen to the standard deviation? Well, let's start off by finding the standard deviation of the population. We find it to be 102.9986. We compared this to the standard deviation of the sample means when we had samples of size 5. Whoa, it's not even close. What about when we had samples of size 10? Well, it's still not close. In fact, it's smaller. The sampling distribution standard deviation is even smaller for samples of size 20, and size 30, and size 50. We can even see this in the histograms. Notice how the spread is decreasing when the sample sizes increase. Okay, so we know that the standard deviation of the sampling distribution doesn't equal the standard deviation of the population. But that doesn't mean that there isn't a relationship. It's a little complicated, but the relationship is as follows. The standard deviation of the sampling distribution is equal to the population standard deviation divided by the square root of the sample size. What we've just demonstrated is a central idea in statistics. It's called the central limit theorem for means. The central limit theorem for means states that if we have a sample mean, x bar, from a large, simple random sample from a population whose mean is mu and whose standard deviation is sigma, then x bar has an approximately normal distribution, with mean mu sub x bar equals mu and standard deviation sigma sub x bar equals sigma over the square root of n. Now there are two related points. Generally, unless the population is extremely skewed, a sample size of n greater than 30 is sufficient. The central limit theorem still applies even when working with a small sample size, as long as it can be assumed that the overall population is approximately normal. Okay, let's write the central limit theorem a little more briefly. X bar is approximately normal with mean mu and standard deviation sigma over the square root of n, as long as n is greater than 30 or the population is known to be normal. Note that this now gives us the ability to compute probabilities involving X bar. Let's just jump into an example. A population of male penguins had a mean body mass of mu equals 4,136.662 grams, with a standard deviation of sigma equals 102.9986 grams. A sample of n equals 70 penguins is selected. What is the probability that the mean of the sample is less than 4,150 grams? Okay, let's first look at n, the sample size. Since n is greater than 30, we know that the central limit theorem kicks in here. This tells us that x bar is approximately normal with mean mu and standard deviation sigma over the square root of n. Let's define n to be 70, m to be 4,136.662, and s to be 102.9986 divided by the square root of n. The probability that x bar is less than 4,150 is p norm 4,150, m, s. We find the probability to be 0.8607. Remember here that the standard deviation we plugged into the p-norm function was the population standard deviation divided by the square root of n. Suppose that a new sample of n equals 150 penguins is selected. What is the probability that the mean of the sample is between 4,120 and 4,160 grams? We know that the central limit theorem works here because n is greater than 30. So let's redefine n to be 150. The probability that x bar for the new sample is between 4,120 and 4,160 is p norm 4,160, m, s minus p norm 4,120, m, s, which is 0.9735. A new sample of n equals 16 male penguins is selected. What is the probability that the mean of the sample is between 4,120 and 4,160 grams? Okay, here we have to be careful. It would be an easy mistake to go in and redefine n to be 16 and just rerun the commands, but that would be a mistake. Do you know why? It's because we have a sample size that is too small. Now, if we knew that the population was normal, we could get away with it. But that's not the case here. So here we're stuck. We can't find this probability. And this is an example of how statistics can sometimes be tricky. We could run the R commands and get an answer, but that answer would basically be meaningless. Let's consider a new example. In a large study of 4,912 people on sodium-restricted diets, the amount of sodium excretion in milliequivalents per 24 hours was recorded. I'm going to pull in the data from the study, and then we'll take a quick look at it. Suppose that a group of 40 individuals are selected to determine the effect of sodium restriction on blood pressure. What is the probability that their average sodium excretion is no more than 56.2? Well, we first note that our sample size is 40, which is large enough to be able to find the probability using the central limit theorem. Let's define n to be 40 and m to be the mean. Also, let's let s be the standard deviation divided by the square root of n. The probability that the average sodium excretion is no more than 56.2 is given by p norm 56.2, m, s, which equals 0.1944. Suppose that as a control measure, if the average sodium excretion for the 40 individuals measures above 59, then it is determined that at least one individual is non-compliant with the sodium-restricted diet. What is the probability that such a determination is made? Okay, we need the probability that the sample mean is at least 59. This is given by 1 minus p norm 59, m, s. We find this to be 0.2432. It has been suggested that a measurement of 59 from this last example is too restrictive. What should the cutoff be so that there is only a 3.5% chance of making the determination of at least one individual being non-compliant? So here we want to know what the cutoff should be so that only 3.5% of the time X bar will exceed it. In other words, we want the 96.5th percentile of X bar. We run the Q norm 0.965, m, s command to find that the cutoff should be approximately 61. Let's take another look at the central limit theorem for means. Note the form of it. We are saying that X bar is normal with a given mean and standard deviation as long as certain conditions are met. We are now going to talk about an analogous theorem that deals with proportions. I'll start by erasing certain parts here of the theorem. Now, instead of finding probabilities involving a sample mean, we are going to be working with sample proportions. So the questions are, what should we put down as the mean? What should we put down as the standard deviation? What are the conditions that have to be met? Here we're going to assume that we have a population where we know the population proportion. For example, maybe we know that 40.1% of adults in the US delayed getting health care because of the COVID-19 pandemic. In this case, the population proportion is p equals 0.401. When we draw a sample, we will also know n, the sample size. So in the central limit theorem for proportions, we expect for it to involve the quantities n and p. I'm going to skip over the details and just fill in the missing pieces. The mean of the sampling distribution for p hat is p, the population proportion. The standard deviation is given by a little bit of a complicated formula. It's the square root of p times the quantity 1 minus p over n. Now the conditions that must be true in order for p hat to be approximately normal are that n times p must be greater than or equal to 10 and n times 1 minus p must be greater than or equal to 10. So let me just say a word here about these. What these conditions are doing is trying to prevent any skewness from creeping into the sampling distribution. To see this, imagine that we have either a really small or a really large population proportion, maybe something like 0.5%. Then by requiring that n times p be at least 10, this is just making sure that we have a large enough sample size to adjust for such a small p. Okay, so let's put it all together. We have the central limit theorem for proportions, which states that the sample proportion, p hat, is approximately normal, with mean p and standard deviation square root of p times 1 minus p over n. As long as n times p is greater than or equal to 10 and n times the quantity 1 minus p is greater than or equal to 10. Let's jump into an example. In 2020, it is estimated that 40.1% of adults in the US delayed getting health care because of the COVID-19 pandemic. A sample of n equals 20 US adults is selected. What is the probability that the sample proportion is between 40% and 50%? We first check the assumptions. Here, n equals 20 and p equals 0.401. We find that n times p is equal to 8.02. Now we don't need to check n times 1 minus p because we've already determined that the conditions are not satisfied. We are not able to find the requested probability here. Suppose now that a new sample of n equals 100 US adults is selected. What is the probability that the sample proportion is between 40% and 50%? Okay, so let's try this again. Here, n equals 100 and p equals 0.401. We're going to check the assumptions. Now, n times p is equal to 40.1, and n times 1 minus p equals 59.9. Since both of these values are greater than or equal to 10, we know that the central limit theorem applies. Let's go ahead and define the mean and standard deviation. So we have the mean, m, which equals p, and the standard deviation is the square root of p times 1 minus p over n. Just for fun, let's take a look at m and s just to see what they turn out to be. Okay, so at this point we know that p hat is approximately normal, and we've determined the mean and standard deviation. The probability that the sample proportion is between 40% and 50% is p norm 0.50, m, s minus p norm 0.40, m, s. We find it to be 0.4864. Alright, one last example. A study of a population of 1,152 Asian elephants was conducted. Let's pull in the data and take a look at it. I'm going to call my dataset EL. Also, note the name of the variables in the dataset. I want to answer a couple of questions involving sample proportions. What I'm interested in is the set of elephants that are younger than 15 years old. So I need to determine what proportion of the elephants from the population are younger than 15. I found the easiest way is to set up a logical condition like this, where we set the age variable in the dataset less than 15. This returns a list of trues and falses. Now we need to count up the number of trues. Behind the scenes in R, a true carries a value of 1, and a false carries a value of 0. So if we take the sum, it will just count up how many trues there are. So I can find the number of elephants in my data array that are younger than 15 using the following command. We find that there are 824 elephants in the population that are younger than 15. Since there are 1,152 elephants altogether, the population proportion of elephants younger than 15 is 824 over 1,152, which is 0.7153. We'll define this as p, the population proportion. Now, in our first question, we suppose that a sample of 40 elephants is selected from the population, and we want to know the probability that at least 75% of the elephants in the sample are younger than 15. We define n to be 40, so let's check the assumptions. We find that both n times p and n times 1 minus p are at least 10, so we can proceed. I'll go ahead and define the mean and standard deviation. Now we want to know the probability that p hat is at least 75%, or 0.75. So we have 1 minus p norm 0.75, m, s, which is equal to 0.3133. Would it be unusual if fewer than 24 of the 40 in the sample were younger than 15 years old? So 24 out of 40 is 60%, or a proportion of 0.6. So we want to find the probability that p hat is less than 0.6. Running the p norm 0.6, m, s command, we find the probability to be 0.053. It's not quite at the point where we'd call it unusual, but it's probably safe to say that it's not exactly a common event either. So now we've explored the relationships between population parameters and sample statistics. In this lesson, we assumed that we knew the parameters. Later, we'll go in the other direction. We'll start with a sample and then use these relationships to make educated estimates about what the population parameters are. And that's really the crux of statistics, using what you see in a sample to make inferences about populations in general.